selection question.
There's something about differentiating. I have to do some calculus. I'll write that down.
So there's an X and a Y.
Okay, so what we're going to go through together today is a review of the complex numbers unit. So it's a short unit, right? Just chapter 4. And so we'll talk about what skills are required, we'll talk about revision resources, and then we'll go over some questions together. And the questions we'll go over together, I've chosen some fairly easy ones just because I want it to be about skills rather than about complexity. And you can get the complexity. And the complex numbers, let me say this, that can be a very complex topic because when you have a look at some of the exam questions, like we've done all of these exercises, we've just chunked. Okay, so 4A is just one skill, 4B just one skill. Whereas in the exam questions, they combine all of them, and not only that, they'll combine them with polynomials and so forth. Now, we are not assessing polynomials in this unit, okay, in this test, so you won't be required to remember any of that. And we are not assessing things like triangle inequality. That's going to pop up in vectors. So when you hear that, you can just ignore that. We're just focused on the chapter 4 content of complex numbers. Okay, so I've got the test conditions written there. So Thursday of week 1, lesson 7 and 8. We've got 70 minutes, around 50 marks. Once I've written the test, I'll let you know the precise number. You're allowed to bring 1 page of handwritten notes. You're allowed to bring the formula sheet. Okay, and so everything on the formula sheet, including the trig ratios, cosine rule, and so forth, all of that is assumed knowledge that you know how to use that and can use that. So let's leap in then to the content. So you can see I've just got the chapter summaries listed there, and then in chapter, so the content, and then as far as the skills go, what we're required to do, sketch complex numbers on the argument plane in both Cartesian and polar form, determine the modulus and argument of complex numbers in Cartesian and polar form, convert between polar form and Cartesian form, perform basic proofs around the properties of polar form involving modulus and argument, find the nth roots of complex numbers, and then graph complex sets and loci in the complex plane. And those skills basically align with the content written there. Okay, as far as revision resources go, I've given you 5 tests today. So all of the tests I've given you have relevant questions. The 2020 test does include some polynomials questions, not many, most of it's complex numbers, but there are some polynomials questions in there. So you can avoid them, that's absolutely fine. Just focus on the complex numbers stuff. And then when we come back, we can go through the 17 and 21 tests. I'll also point out at the back of your notes book is a series of exam questions that I've plucked from heaps of past exams, and that's a really good example of how they ask complex number questions. I really encourage you to work through those, and you can find work solutions to those exam questions and the tests on the OneDrive. And then of course we've got the chapter review set questions. I had a look, all of them are relevant. It goes without saying, I think you don't have to do induction in this test either. Okay, so if you look at PMI, they've got some complex number proofs around PMI. We're not doing induction, we're not doing triangle inequality, and we're not doing polynomials. So we can disregard those things for now. If you're not sure, ask me, and I'm very happy to tell you whether or not it's testable, whether or not it's part of the unit we're on. Excellent. Are there any questions about content or the test and so forth? Splendid. So let's get into this review. Let's absolutely annihilate it. And we're going to talk about how to use our calculator as well. You know, use our calculator to support us all the time. Whenever you're finding modulus and argument, it's just calculator skills. You're not required to show any working whatsoever. So consider the complex numbers. We've got z is 3 plus 2i, and w is minus 2 plus I. So this is in, both of these are presented to us in Cartesian form. Okay, first part says evaluate and draw z multiplied by the conjugate of w. Okay, so that means 3 plus 2i multiplied by the conjugate of w means we change that to a negative. Okay, minus 2 take I. Then we're just going to perform FOIL. So let's speed run this question. Speed runs are very entertaining. So plus 2. I've got minus 4 take 7i. Okay, draw it on the Argand plane. So we have minus 4 is the real component, and then minus 7 is the imaginary component, and so that's going to be z conjugate w. Okay, part B, determine the modulus and argument of z and w. So I think the fastest way to do this is in our calculator, type in 3 plus 2i and convert it to polar form, because polar form expresses to you straight away modulus angle argument, doesn't it? So 3 plus 2i, option, complex, convert, and then angle cis theta, convert to polar form. I'll put those steps up just to refresh us. So 3 plus 2i, and we go option, complex, across, option, complex, then the across button, and then we have this one, r angle theta. So we'll press that, and I've got root 13, cis, and then my angle in radians, make sure we're in radians, 0.588. Unless stated, assume radians for both methods and spec. Always assume radians unless otherwise stated. Okay, now how would we get the modulus manually? Okay, the modulus manually is going to be the square root of the vertical component plus the horizontal component. So that's root 9 plus 4 is 13. And the argument, how do we get the argument? Well, it's across 3 and up 2. We want that angle, so it's this is a right angle triangle, this is our opposite side, our adjacent side. So it's tan of O on A, O is 2, A is 3, so tan is 2 on 3, and inverse tan of 2 on 3 would be 0.588 radians. And just so you remember, so we're answering the question, aren't we? So the modulus of z, we can say is root 13, and the argument of z is 0.5880, so 0.588 to 3 significant figures. Okay, so that's the modulus of z, and then we can repeat the same for w just using your calculator. So I'll type that in quickly. So we've got an answer, minus 2 plus I. And I've got 5, root 5, so that's part A. And then modulus of W, root 5, and the argument of W, we've got 2.677. 3 significant figures, 2.68. Okay, so sometimes it'll spit it out as a irrational number, and every now and then, if it's on the unit circle, or it's a multiple of number on the unit circle, or a nice factor, I should say, of one on the unit circle, it will come out nicely for us as a fraction. All right, let's go into a proof then. There will be some of these proofs. So we have no erasers. There's some tissues there. So whenever we're required to do a proof, all right, we just start with the left-hand side, match it, and see how far we can take it, see if we can match it to the right-hand side. So this one we're doing is prove that the modulus of z squared equals z times the conjugate of z. So we need to define this complex number. So anything will do, let z equal a plus bi, okay? And then we'll focus on the left-hand side. Is the modulus of a plus bi, which is the square root of a squared plus, sorry, the modulus of a plus bi squared, square root of a squared plus b squared, which is a squared plus b squared. Okay. So we'll leave the left-hand side as it is for now, and we'll jump over to the right-hand side. All right, when we're doing a proof, we don't always have to follow the left-hand side through the whole way. We just need to show that they're equal at some step along the way. So the right-hand side is z conjugate of z, which is a plus bi multiplied by a take bi. Difference of two squares, that's a squared take bi squared, which is a squared take negative b squared, a squared plus b squared. Left hand side equals right hand side QED. Alright, so we just need to manipulate both sides or one side until we've demonstrated that the equality is true. Good. On to question 3. Convert 2 plus 2i to polar form. Alright, so I'll just go into my calculator. 2 plus 2i, it's going to be 4, and the square root of 4 is, sorry, it's going to be 8. Square root of 8 cis pi on 4. And then we have convert 3 cis of pi on 3 to Cartesian form. So we can do the same thing. We can do this on our calculator or we can do it manually. I'll talk about both first. So the way we would type 3 cis of pi on 4, pi on 3, in our calculator. So this is question 3 part B. 3 cis of pi on 3. Okay, in your calculator what you'll type in is you'll type in 3 angle pi on 3, and then we'll press the convert button to a plus bi. Okay, so that's how we can do it. 3 angle is the shift x, and then we have pi on 3. Good. Now, if you have your calculator in menu, maybe I can show you this. I don't think I've shown you this yet. Everyone press Shift Menu on your calculator, and if we scroll down, you can see there's a complex mode. All right, everyone see complex mode. So whenever you type in a number in polar form, you don't even have to press convert it to complex mode. I've typed the number in polar form and it's converted it immediately to Cartesian form for me. So I've just typed that in and pressed execute. Obviously following that step will still dish out the answer. 3 root 3 on 2i. Okay, how would we do that manually? We would have 3 and then, so 3 is the modulus, and what is cis of pi on 3, but cos of pi on 3 plus I sine of pi on 3. We look at our unit circle, convert the cosine value, convert the sine value, and then distribute the 3. All right, determine the distance between z and w. So this is a skill we did last lesson. So if we have two complex numbers drawn, so let's just say we've got z and w, then the distance between them is equal to the modulus of z take w. All right, so our complex numbers are, and we can do it either in polar form or Cartesian form, and we can do it on our calculator or we can do it manually. Let's recap how we would do it manually, and then we'll just plug it in our calculator, because I don't think it turns out too nicely. So we've got z is 2 plus 2i, so I'm going to have the modulus of 2 plus 2i, okay, the modulus of z take w, take away, and then w, when we convert it to polar form, is, Cartesian form is this one, 3 on 2, take 3 root 3 on 2 i, and then the modulus of that. What we would do following that is collect the real components, collect the horizontal components, and then square both sides. The reason it's going to be a little bit messy is because when I collect the imaginary components, they don't simplify to an integer, and so then we have to perform a perfect square and so forth. Just gets a little bit messy, but the algebra still follows, can be done. Let's just type it into our calculator. So all I'm going to do is type this exact thing in. Okay, there's absolute value on our calculator. We press Option, Calc, we press Option across, Option complex, and it brings up absolute. Option, complex, abs, and then we just type that in, 2 plus 2i, and then take away. Now this negative needs to distribute, so make sure you place brackets around that. 3 on 2. Take 3 root 3 on 2. Pi. 4.625. Units. We're talking about a distance. Very good. Okay, question 4. We're on to nth roots. We have z to the 4 equals minus 4 take 4i. Okay, and we're going to use De Moivre's theorem to find the values of z that satisfy this equation. So the first thing we're going to do is convert that to polar form. Alright, so what's it going to be? 4 squared plus 4 squared is 16, root 32, cis, and then the angle we've got minus 4 and then down 4, negative 2, negative 3 pi and 4, because they're the same value. Alright, so just explain my thinking a little bit there. They've got this negative 4 and then down 4, and then that angle is going to be 3 pi, so the argument is negative 3 pi on 4. And then 4 squared is 16 plus 4 squared is 32, so the square root of 32 is going to be our modulus. And so that's what z to the 4 is. Then let's apply De Moivre's theorem. So we'll have z is this whole thing, the square root of 32, which means 32 to the half. And then we have cis of minus 3 pi on 4. And we have all of that to the power of a quarter, which will be 32 to the power of 1 on 8. So I'm multiplying those powers there. And then we'll have cis of minus 3 pi on 16 plus k2 pi on 4. For k is 0, 1, 2, or 3. Should put my plus k2 pi here. K is an integer. Alright, let's keep going through and solving. So what I'm going to do, I'm going to express them with the same denominator. And this 32, that's 2 to the power of 5, isn't it? So we have 2 to the power of 5 on 8. Cis, and then minus 3 pi on 16, that can stay as is for now. And I'm just breaking it down. I'm going to make them have the same denominator. So multiply this by 4, I have k8 pi on 16. Okay, now they have the same denominator. As I'm subbing in k, the values are going to be very clear. So we'll have 2 to the 5 on 8, cis of minus 3 pi on 16 when k is 0. When k is 1, you'll have 2 to the 5 on 8, cis of, it's going to be minus 3 plus 1 lot of 8, will be positive 5 pi on 16. Does anyone evaluate it? 2 to the power of 5 on 8, cis of, and then we'll have minus 3 pi plus 16. Positive 13 pi on 16, and 2 to the 5 on 8 cis, and when we put in 3, we'll have 24 pi, 21 pi on 16, and here we've exceeded the domain of positive pi, so we're going to take away 2 pi from that one to obtain minus 5 pi. Okay, minus 5 pi. When I take away 2 pi from this angle, I get minus 5 pi, and that puts me in the domain, or the argument of, the domain of an argument for a number in the polar form. Okay, so we've got 4 solutions there, very good. Sketch them on the Argand plane. So we know they're going to be equally spaced apart. There's 4 of them, so they're 90 degrees apart, all of them. And the first one is at minus 3 pi on 16. So that is very, very close to pi on 4, right? So pi on 4 is here, and it's just this side of pi on 4. So I'm going to put it there. The next one's 90 degrees to it, 90 degrees to it, and then 90 degrees to it. And we draw either a circle or we can write the modulus next to it just to illustrate that they're the same length. But this is good to illustrate that they lie in a circle. And the modulus of this circle is 2 to the power of 518. Here's the real component, here's the imaginary component. All right. Okay, that's 4, on to 5. So we have a complex set. We have determined the Cartesian equation. Not even asked to draw it, just determine the equation of this set. Okay, so we know we have the modulus here. So we know z is some complex number x plus I times y. Take 3 plus 2i. We're going to collect the real components and then the horizontal components, imaginary components, 1 plus y plus 2, so 3, good. Square both sides, perform the modulus, and square, we can do that in one step. And there's the Cartesian equation of a circle. So that's our answer to question 5. The circle has a centre, x is 3, y is minus 2, and a radius of 3 units. Okay, and we get to a stage where once we've done quite a few of those questions, we can see, all right, complex number drawn from the point 3, negative 2i, and has a radius of 3, or a modulus of 3, magnitude of 3. Okay, last one. Now this is the one we haven't done. We haven't seen a skill like this yet. It's combining a number of certain things, different things that we've seen before. So we have two complex numbers. We have z1 is 1 take I to the power of n, and z2 is 1 plus I root 3 to the power of n. So this is a past exam question, by the way, where m and n are positive integers. Find z1 and z2 in polar form. Okay, so firstly, 1 take I. The modulus is, so you can straighten your calculator if you like, but you just get good at seeing what the modulus and argument is. Don't get it wrong though. So what this means is root 2 is 2 to the half, and the m goes to the power, and to the angle here. Alright, so that's converted to polar form. And we'll do the same with z2. So it'll have a modulus of 2 and an argument of pi on 3. And I think it goes without saying, like I'll always do both. Minus pi m on 4 is the same as, we can either put the value at the top of the fraction or leave it out the side. They mean the exact same thing. Okay, so that's part A done. Find them in the form r cis theta. If z1 equals z2, show that, okay. So if z1 equals z2, what this means is the modulus of the two complex numbers is equal to one another. So that means 2 to the half m equals 2 to the n. We have the same base, so therefore we can equate the powers. We have half m equals n, and we have m equals 2n. So that's B part 1. Here's A, B part 1. Okay, now B part 2, hence find the smallest positive integers m and n. such that z1 equals z2. Now this is a good example of a question where they're looking for what we call final answer only. Like having marked exams before, in the marker scheme, they'll write something like this, final answer only. And so even if you do no working out and you have the correct answer, you can still get all 3 marks for this question. Obviously, I'm going to make an argument to you, but this is definitely a question that you can solve through trial and error, isn't it? You're saying, I want this complex number to be the exact same as this one. What's the value of n and m that's going to satisfy it? Okay, what's the value of n and m that's going to make it true? So let's make the mathematical argument. So what it means, because the modulus is going to be equal, we can disregard that component. We're particularly interested in the angles, right? So what we'll have is we'll have cis of minus pi m on 4 is equal to cis of pi m on 3. All right. And we also have, we can substitute straight away. We're going to try and, we know m is equal to 2n. So we can reduce the number of variables involved here by either getting rid of m and substituting it for 2n. Now we've only got one variable and we're solving for n. We're saying what value of n is going to make this statement true. Okay, so from here, all right, I'd expect you guys to get this part fine, all right? But from here, there are a couple of ways you could go about it. One would definitely be trial and error. But I think the best procedure is if we divide both sides by this complex number or this one, doesn't matter which way you do it. But I'll show you why. Let's divide both sides by this. Okay. So when I divide the left-hand side by this, what we'll get is we'll get 1. We'll get 1 equals, I'm going to write up here in a bit more in a moment, 1 cis pi n on 3 on top of cis minus pi 2n on 4. Okay, and this is perfect because now we can collect these two complex numbers. So, all right, because if we have cis theta on cis phi, it's equal to cis of theta take phi. So we can collect the argument of these complex numbers, right? So we'll have 1 on the left-hand side, and on the right-hand side we'll have cis of the top argument, pi n on 3, take away the bottom argument, which is minus pi 2n on 4. And by the way, that can be simplified to pi on 2n. So we'll do that up here. Okay, so what does this become? It's become cis of pi n on 3 plus pi on 2n. Okay, now when we collect these, when we're adding them together, we need them to have the same denominator. So I'm going to change this to 2 pi n on 6, and this one will be 3 pi n on 6 equals 1. And so we'll have cis of 5 pi n on 6. Okay, now what's going on over here? This is cis of 2 pi or cis of 0. Like this number over here is some multiple of 2 pi. It's cis of 2 pi. So we need 5 pi n on 6 to equal some multiple of 2 pi. All right. So we've really broken it down to now at a stage where I can take the algebra a little bit further, but I think from here the most intuitive strategy is to go, what value of n is going to give me a multiple of 2 pi? Okay, and it has to be a multiple of 6 because we have a denominator of 6, right? So if I put 6 in, we're going to have 5 pi. Now, 5 pi takes us to the angle -1. So that's not the correct answer. All right, so then the next multiple of 6 would be 12. And if I have 12 on 6, all right, that's going to give me 10. 12 on 6 is 2. 2 times 5 pi is 10 pi. 10 pi is a multiple of 2 pi. All right, so the value for n is 12. Now, how else could we derive that? Like if we're solving here for n, what we'll have is n is 6, what we'll have times both sides by 6, so we'll have 6k 2 pi on, 12k pi on top of 5 pi, and I'm not mess that up. Go slowly, I'm trying to do it too quickly. So we'll have 5 pi n equals 12k pi, and then n is 12k on 5. All right. Because we divided both sides by pi. I don't see how that helps us. 12k on 5, what are we missing? N has to be a positive integer. K is an integer as well because it's a multiple of 2 pi. So we're saying what maybe let's just go back to this step. Are you guys happy with why n has to be 12 here? Or I can try to explain that part again. You're okay with it? Yeah. Jack, were you sure? Yep. All right. Cool. I'll have a think about how to break that down further, but I think there's a bit of like intuition there because it's a multiple of 2 pi because the cis function is periodic. All right, so that's everything that's going to be in there. You know, those are the techniques. But yeah, up to you how you use this time. Definitely in the holidays, want you to do